properties of eigenvalues and eigenvectors. The first property is if lambda 1, lambda 2, etc. lambda n are the eigenvalues of a matrix A, eigenvalues of a matrix A, then lambda 1 power m, lambda 2 power m, etc. lambda n power m are the eigenvalues of matrix A power m. So what they given, eigenvalues of A are lambda 1, lambda 2, etc. lambda n. Then we need to prove the power of A, eigenvalues of power of A. So proof, suppose if lambda is an eigenvalue of A, lambda is an eigenvalue of A, so we know the relation Ax is equal to lambda times x. So now pre-multiply this equation by A, so we will get A into lambda times x. Take this equation number 1. So this left hand side will become A square x, right hand side take lambda outside because lambda is a scalar, then Ax from 1 lambda into this will become lambda x, right? So this implies this equal to lambda square x. So now we have the relation A square x is equal to lambda square x. So compare with the first equation. When lambda is an eigenvalue of A, we have the relation Ax is equal to lambda x, right? So lambda is an eigenvalue of A. Compare this equation, compare with this equation. Now lambda square is an eigenvalue of A square. Okay. So lambda square is an eigenvalue of A square. Next, suppose I want to find the eigenvalue of A cube. So take this equation number 2, multiply this, pre-multiply A in the equation 2, we will get A into A square x is equal to A into lambda square x. So left hand side is A cube x. So here lambda square is a scalar, so we can take outside. So Ax lambda square into lambda x by 1. So this will become lambda cube x. So now we have the relation A cube x is equal to lambda cube x. Therefore lambda cube is an eigenvalue of A cube. Similarly we can extend. So finally we will get A power mx is equal to lambda power m x. Therefore lambda power m is an eigenvalue of A power m with the same eigenvector. So eigenvectors are same for A and A power m, but eigenvalue, if you want to find the eigenvalue of power of a matrix, then raise the power of eigenvalues. That's enough. Okay. So hence lambda 1 power m, lambda 2 power m, etc. lambda n power m are the eigenvalues of A power m. The second property is if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. Proof, simple. When lambda is an eigenvalue of A, then we have the relation Ax is equal to lambda times x. Now pre-multiply this equation by A inverse. So A inverse Ax is equal to A inverse into lambda times x. So this will become A inverse A is nothing but I, identity matrix Ix. This will be lambda into A inverse x. Since lambda is a scalar, so you can now take outside, and then this will be x lambda into A inverse x. 1 by lambda into x is equal to A inverse x. Therefore A inverse x is equal to 1 by lambda times x. Suppose this is the first equation. So Ax is equal to lambda x means lambda is an eigenvalue of A. So now compare with this equation. 1 by lambda is an eigenvalue of A inverse. 1 by lambda is an eigenvalue of A inverse with the same eigenvector x, with the same eigenvector yes, x. Next example, if 2, 3 are the eigenvalues of a matrix A, then what are the eigenvalues of A square, A power 4 and A inverse? Answer. So 2, 3 are the eigenvalues of A. For A square, just raise the powers of eigenvalue. So 2 square, 3 square, that is, this implies 4, 9 are the eigenvalues of A square. For A power 4, just raise the powers, eigenvalues of power up to 4. So 2 power 4, 3 power 4. This implies 16, 3 power 4, 18. So these are all the eigenvalues of A power 4. For A inverse, 1 by 2, 1 by 3 are the eigenvalues of A inverse. Similarly, if you want to find A power minus 2, 1 by 2 square, 1 by 3 square. So that is 1 by 4, 1 by 9 are the eigenvalues of A power minus 2. Next property, suppose A is a triangular matrix. The eigenvalues of A are just the diagonal entries of A. Proof. Suppose A is a triangular matrix. Take any either upper triangular or lower triangular matrix. A13 0, A22, A23, 0 0, A33. This is upper triangular matrix. So generally we know that the characteristic equation of a matrix is A minus lambda, determinant of A minus lambda equal to 0. From this we have to find the third degree polynomial, and then the roots of this equation are called the eigenvalues of a matrix. So write the characteristic equation. So you will get A11 minus lambda, A12, A13, 0, A22, A23, 0 0, A33 minus lambda. Here also A22 minus lambda, right? A22 minus lambda, A33 minus lambda equal to 0. So now find the determinant. So you can express using the first column, A11 minus lambda into A22 minus lambda into A33 minus lambda minus 0. So this equal to 0. This implies lambda value is A11, A22, A33. These are all the diagonal entries of a given matrix. So similarly we can extend for any n cross n matrix. So hence it is proved. Okay. Example, suppose A is equal to 2, 3, 5, 1, 2 some values 0, 0, 0. Then eigenvalues are 2, 3, 5. Or A is equal to, suppose, a lower triangular matrix 2, 3, 5, 1, 2, 4, 0, 0, 0. This case also the eigenvalues are 2, 3, 5. Suppose it is a diagonal matrix. Simply it is a diagonal matrix. This case also the eigenvalues are A are 2, 3, 5. Thank you.